Welcome back, and I'm glad you're here. I wanted to talk about number systems at a pretty high level, although the topic could be a much more serious matter that we could spend weeks talking about, as a segue to our first real programming practice that we're going to work on together here. So, when I mean number systems, I'm referring to how we actually represent our numbers. We're pretty familiar, I think, with the decimal number system that we use to count things in day to day practice. It's actually just a specific case of a more generalized number system. So, when I refer to something as being decimal, actually, another term for that is base 10. And that means that each digit has 10 unique values and is also going to be a power of 10. So, I refer to something as being decimal, it's actually synonymous with being base 10. So when we look at a larger number like 4,125, and I know you know this, but we could actually break that down by the individual digits. That first four actually represents 4,000. That next one actually represents 100. The two represents 20, and that five represents the units digit of five. And we can think of that more generally as that 4,000, or that four is 4 times 10 to the third plus 1 times 10 to the 2 plus 2 times 10 to the 1 plus 5 times 10 to the 0. And so more generally, we can write our decimal or our base 10 numbers as a summation of the individual terms multiplied by that 10 to the equivalent power of I, where b sub I is the ith digit of that number, and we have that 10 to the I exponent there. And it can be for an arbitrary number of digits here. But the takeaway is that 10 is also actually an arbitrary number choice for the number of our digits. Any thoughts about why it's base 10 by default that we all use versus base 9 or base 11? Um, Kind of gruesome picture my show here is someone saying, well, let's all go to base 12. Anybody? Anybody? Yeah, we have 5 fingers. That's gross, I know. 5 fingers on our hands, and 10 fingers total. When we were counting, it makes sense to count in terms of multiples of our 10. I think the takeaway is not that 10 is some magical number, but that we can actually generalize it more. That base does not have to be 10, and we can actually represent numbers via any arbitrary base. So instead of b sub I times 10 to the I, it's b sub I for the individual digit times base to the power of I, where when the base equals 10, that's our decimal numbers. When our base equals 2, that's our binary numbers. 8 corresponds to octal representation, 16 for hexadecimal. Any arbitrary number for our base is valid to represent our numbers. But those three are the three we're going to commonly use here. Beyond our base 10, we're going to use 2 for binary, 8 for octal, although a little bit less commonly, and 16 for hexadecimal representation. So I'd like us to undergo a brief problem solving exercise here. Not a coding exercise, those are slightly different things. To design a method that would eventually become a program that takes as input an integer value and returns as the output the sum of the integer's decimal digits. So for example, if the input was 257, then the output should be 2 plus 5 plus 7, the output should be 14. Let's not worry about the C program as of yet. Let's just think more about like that problem solving process. I like to do pencil and paper when I'm doing this. So for me, it's more about what is the problem? How would I go about conceptually solving it? Because if I can't solve it on pencil and paper, this is at least my limitation. If I can't solve it on pencil and paper, I'm not going to be able to solve it with a program. The program is harder than the pencil and paper version. I have to understand conceptually what I'm trying to do, and then I worry about the syntax, and usually I can figure out the syntax after the fact. So usually you'd want to start with maybe a restatement of your problem. And if our input was 257, and I won't be writing a lot on this because it is awful, my handwriting, our output would be 14 because that's the sum of the individual digits. What would we have to do to solve this? I need to sum the individual digits. Write that down, whether that's a note or that's the actual requirement. And to sum those individual digits, I need to be able to get those individual digits. Right now, when we're thinking of programming and problem solving, that's got to be the next logical leap. I can't always make that leap for you. I mean, certainly when you ask questions, I'll help you make that leap, but we have to be able to make that logical leap. I have to add up the individual digits, so I have to somehow access and get those individual digits. I don't necessarily need to store them somewhere, but I need to be able to access those digits to be able to do our addition of those individual digits. Well, what are the individual digits? I know by looking at this number or any arbitrary number, we can see it when we know it. 257, our individual digits are our 7, our 5, and our 2. And I think it's important to note that, whether we do 2 plus 5 plus 7, it's going to be the same as 7 plus 5 plus 2. We haven't solved the problem yet, but I want you to go through this exercise when you work on a new program. Before you worry about include standard IO and what printfs I'm going to have, that's all well and good. But if you don't know how you're going to break down the problem, you're going to be really frustrated, first off. We can't write code if we don't know what problem we're trying to solve. So I need to access those individual digits, and then I can worry about adding them. Well, how can I access those individual digits? We saw it briefly in the prior part of the lecture where we were generating random numbers, and to make them smaller, we were doing a modulo operator or a remainder operator. I think it's fair to say that this is a well known computing trick. I don't necessarily expect you to know it from base principles, but if it turns out we take a value like 257, call this our observation, and we do a remainder operator, not a division operator, but we do a remainder operator by 10, what's the result going to be? Well, what's the remainder when we divide something by 10? It's going to be something in the range 0 to 9. In this case, we do 257 divided by 10. We get 2. We get our 5, and we then get a remainder 7. I guess this is a computing trick, so it's not necessarily something that you'll know from just base understanding of what we've covered so far. But yeah, we can actually access that 7 by taking that num, that input, whatever it may be, and doing a mod 10. And that gives us the value of 7. That gives us the value of 7. Can we do mod 100 then to get the value of 50? Well, we take 257 divided by 100. We would get 2 with a remainder of 57. So the remainder isn't exactly right. Maybe sometimes we want that for some other purpose, but for this purpose, no, that's not quite right. Hey, it was worth a shot. I mean, not every idea you come up with is going to be correct in the first place. But let's look back at what happened when we did that division and then took the remainder. We took 257, we divided by 10. I somewhat sloppily came up with 25, remainder 7. Hey, that 25 is also useful. Now when we have that 25, we can do the modular operator. So if we were to first take num divided by 10 to get to 25, we can then do num modulo 10 with that remainder to get the value of 5 back out to add to our 7. And we could probably do that for every digit, right? As long as we keep dividing by 10, we can use the mod operator to get that least significant digit of our value and then add it back out. Whether we divide by 10 twice or divide by 10, take the original value and then divide by 100, we get the same exact result. So in terms of problem solving exercise, yeah, we haven't written a line of code yet, but that's what I want you to do, that kind of thing. What are my variables? What is my input? What does my output need to be? We haven't exactly solved the problem, but we came pretty close to solving the problem there. We can then write that code that does maybe a scanf to read in a number, does mod 10, adds it to a sum, divide by 10, mod 10, adds it to a sum, rinse and repeat, and get our values back out. We're going to do a slightly different example here in just a moment, but go back to this problem solving exercise when you have to do the equivalent programming practice assignment that you have. So that's our general number systems where it's base to the power of I, and I mentioned binary is extremely common. Not just because we're representing our data in memory as our ones and zeros, just because it's a very common way to represent any variable that we may have here. So if we have our base as 2, all of our individual digits would correspond to increasing powers of 2. So 2 to the 0, 2 to the 1, 2 to the 2. As programmers, we tend to memorize those common powers of 2 because we just see them over and over again in our code. So if this was our value where we use the 2 subscript to represent that it's not a decimal number anymore, it's not a base 10 number, it is a base 2 number, what would this actually correspond to? 0 times 2 to the 0, plus 0 times 2 to the 1, plus 1 times 2 to the 2, which is 4, plus 1 times 2 to the 3, which is 8, 16, 32, 64. Our number would be 4 plus 8 plus 64 in our base 10 system 10. What if this was a number? Take a moment and convert this number to a decimal equivalent. And if you've got that, then you don't have to worry too much more about binary representation. You understand well enough. And I would also mention that we have a whole course that talks about digital logic, and it's not just binary number systems, but that's a big part of the course. How do we do math and other things in our actual binary logic itself so that we can build computers that do that type of arithmetic? I had mentioned hexadecimal representation. The only thing that makes it any trickier than base 10 or base 2, well, first off, multiplying powers of 16 is a little bit harder to do in our head. That's one reason. And secondly, we don't have enough digits to represent the 11, 12, 13, 14, and 15 numbers. So when you see any data that's being printed out and you're seeing A's, B's, C's, D's, E's, and F's, but nothing else beyond those and those 0 through 9 values, it's very likely that data is in hexadecimal format because we use the A to represent 10, B for 11, up through F for 15. So really high numbers would have a lot of F's in it because that has a lot of ones in it because it corresponds to 15 out of 16. Otherwise, though, the conversion back and forth is exactly the same. We have this arbitrary 1, 2, 3, 4, B, E, E, F number here. It'd be F, which is 15 times 16 to the 0th power, plus E, which is 14 times 16 to the first power, etc., for the rest of the digits to get to, in this case, a relatively large number corresponding to our base 10 equivalent. Computers are doing their work using binary representation. Our ones and zeros are stored in memory. Hexadecimal is very useful, though, for just representing larger binary numbers because it just can be very difficult to deal with a long string of ones and zeros. It turns out it's very easy to convert between binary and hexadecimal because each grouping of 4 binary digits corresponds to a single hexadecimal digit. So it's arguable, I guess, but this representation for the same number is a little bit easier to deal with, to interpret, to just process in your mind than this equivalent base 2 number. And that conversion back and forth is very straightforward. We group each 4 digits. We should start from the least significant to the most. This is 0, 1, 1, 1. Very soon you'll learn, oh, that's 7. Because it's 1 plus 2 plus 4, that's 7. The next one is 0, 1, 1, 0. That's 6 because it's 2 plus 4. The next one is 0, 1, 0, 1. That's 10 because it's 8 plus 2, and that's going to correspond to our A value that we have here. You'll get very good at kind of converting those values back and forth. We use hexadecimal mostly because it's relatively straightforward to do that interpretation of the number and going back and forth between base 2 and base 16 in our head. Base 10 is also still extremely common because that's how we think about numbers quite commonly, but oftentimes we need to have our data in binary format. And while I don't want to get into all the details of how we do it with arithmetic, but the basic rules that we follow for our general decimal arithmetic, we can follow those same rules. And computers do the arithmetic themselves in binary because it actually simplifies the digital logic required. But our addition processes are actually quite similar. When we're adding 89 to 3 in our base 10 math, our grade school math, there's more than one approach, but a very common approach is to go from least significant digit to most significant digit, right? We take 9, we add it to 3, we get 12, so that's 2. We carry the 1. We then get 1 plus 8 to get 9. We actually do the same exact thing with our base 2, our binary representation. We go from right to left, least significant to most significant. We take 1 plus 1. We get 0, carry the 1, because that's 1, 0. That's 2 in our base 2 representation. 1 plus 0 plus 1 is 0, carry the 1. 1 plus 0 is 1, then with no carry. And the math works out. That if this is 89 in base 2, this is 3 in base 2, this does turn out to be 92 in base 2. There's some optimizations, but otherwise that's how computers do arithmetic. The same way you and I do our arithmetic, bit serial fashion, and we kind of propagate our carries on as we're doing our addition. We do have to be careful about overflow in our programs, though. While logically, that order of operations is exactly the same as when we're doing our own base 10 arithmetic. In practice, we have these data types in C, and they're limited to a fixed number of bits. Our cars are 8 bits, they will not be 9. Our shorts are 16 bits, they will not be 17. And so when we're doing our math, we have to be careful about overflow because as part of the specification, for better or for worse, C as a program does not care about overflow. And the following code shown down there is perfectly valid C code, and most or any compilers that I'm really aware of will not even give you a warning when you have that code example there. Let me bring up that example briefly. This is overflow example. We start with an unsigned car, so that's a value between 0 and 255. And again, as implemented, it's this binary arithmetic when we do this addition. The significant bit, add the zeros and ones, propagate those bits on. It turns out we add a value and it requires one more bit than we actually have to store it. If A was 253 and we add 3 to that value of A and store it in B, my comment here says, uh-oh, and it is uh-oh. Well, what'll happen? Okay. A is 253. We add 3 to it, we get 256. But the maximum value we can store in that 8-bit data type is 255. It is comparable to your odometer resetting, where overflowing, we had that extra bit. C doesn't throw up an error. C doesn't throw up a warning for us. We actually get a result that when we add 253 plus 3 with our unsigned car type, do we know what we get? That's right, we get 0 back out. That seems like a problem, right? And if you're looking at that and panicking a little bit, it is a problem. It is a fundamental challenge in the selection of our data types. We should only use that unsigned card type if we're absolutely certain that we'll never need 256 in any of our computations, not just as an end result, but in any sort of intermediate computations as well. When you are in doubt, well, just don't do that. Use ints. Ints are okay, at least for this small example that we have here. It may not be the case for all examples, but certainly for this example, we can add 253 plus 3 and get the correct result of 256 back out. So hopefully that doesn't cause any stress or extra panic. We have to be aware of that. I don't set up any programming practices, at least early on, that you will encounter that. But as you're writing your own code later on, you do have to be aware of your data types and their limitations. And those can be a little hard to track down. Yes, this program should print 256 and it prints 0. Yes, and we caught it. We see that it was a problem. We fix it very quickly as well. Other programs, that'll be one computation across 100 million computations your program is doing. Will you catch it or not, or how much time will it take you to catch it? That can be pretty hard to track down. So let's end today with a final problem solving exercise where we're doing something kind of similar to what we did when we were trying to add the individual digits. Our input's going to be some decimal number. Let's assume it's greater than 0, so it can be an unsigned integer type. And what I want is, instead of adding them together, I just want to print out of the individual digits, both the binary digits corresponding to that number, the decimal digits, and the hexadecimal digits. We haven't covered anything about control statements yet. That's going to be the next topic. So we can't use looping structures or if statements and things of that nature. So can we do this without having that in place? So our input is going to be a number, and our output is going to be a printout of the individual digits, the binary digits, the decimal digits, and the hexadecimal digits. Here, although I said, don't start coding until you have, an understanding of the problem in more depth, I think in the interest of time, it's okay to say, let's start some of the boilerplate code that is going to be so common in all of our programs. We have a program that needs to have a number, so let's do it. Enter the number to print out. And while I said any unsigned number greater than 0, it always has to be a limited range. For now, let's just say that unsigned car range, 0 to 255. Then we would follow that with a scanf call. So we do a little printf that's like the prompt, and this is such a common, design pattern. Printf a prompt, scanf the actual request for the number, and we would pass it using an ampersand symbol, actually the pointer to that value to be read in. And that's a good reminder that we haven't actually declared that anywhere. So let's actually declare that value. That's our value num. somewhere we have to write down our goal. Print out the individual binary digits. Well, how do we do that? Let's go back to this example where we were adding digits, but it was the same concept, right? Here it was add up all the individual decimal digits. Our input was 257, which ironically would be too large for this example, but actually our code should still work. 257, we first had to grab the 7. How did we grab the 7? We did mod 10 operator because that was the remainder when we divided by 10. Then we divided by 10. Then we did mod 10 again and just repeated that until the number was done. It was all used up. We could do something very similar here. Instead of mod 10, though, that gives us the decimal digit. Can we think about what would give us the binary digit when we would take this input number? And going back to our specification here, print out of the binary digits, decimal digits, and hexadecimal digits. Well, print out the individual decimal digits, and then we'll do print out the individual hexadecimal. If we want to actually print out the number as either of those formats, we can do so, right? There's a %d, let's say you entered %d. That's a common little debugging prompt. Hey, did I actually enter in the num I thought I did? That gives us the decimal value. Let's do 257, right? You entered 257. We can also do it as hex. %x gives us the hex version of it. Well, let's do it again. And that turns out to 101 makes sense. That's 256 plus 1. So 101 in our hex. Okay, fine. That feels like kind of cheating. We'll keep that individual prompt there. We had this logic for doing %10 to get the individual decimal digits. Before we worry about the next part, let's do that. Let's declare a digit. We'll talk about where it's best to declare our variables. For now, let's declare them at the top of our function. Later on, we'll see that's not strictly necessary, but for now, let's do that. We'll say digit equals num mod 10. That's our first digit here. And actually, just to be safer than sorry, let's create a backup of that num because this is gonna change the value of num. So let's have a backup num, and let's restore that backup here. Okay, digit equals num mod 10. We can now print out that individual digit. Let's create a prompt though so it makes sense what it's doing. Printf decimal digits are %d. Let's add a little space, and we want to print out that individual digit. Going back to our logic here, we had to do two things. %d to get the individual digit, which we can now print, and then divide that value by 10 so we can kind of shift things along, and we're now at 25 and not 257. So we've talked a little bit about this syntax, but it would be num is equal to num divided by 10. Take the value of our number that we entered, divided by 10 if it was 257. That integer division by design does not do any sort of keeping of the result to the right of the decimal point. So 257 divided by 10 would give us 25. If you do it again. Well, now let's start copy pasting, right? So we can be a little bit more effective as a programmer here. Enter in our number. You entered in 257. Decimal digits are 7, 5. Well, it's printing them backwards, but we never said we cared about what order we're printing out the decimal digits here. That looks pretty good. Let's keep that going. We don't have for loops, although if we learned that would make this code a little bit cleaner. Enter in 257, 7, 5, 2. Of course, the code said enter something in the range 0 to 255, so let's do 254, 4, 5, 2. That also kind of gives an answer to the question. If we're limited to 0 to 255, we know exactly how many times we have to run this code. It's between 0 and 255. There's only going to be 3 decimal digits. That was our logic for doing the decimal digits. It's not correct to copy paste that for our binary digits, but we can kind of start with that. Instead of printing out decimal digits, our binary digits are here. Logically, we did mod 10 operator to get the base 10 digit. We can do the same exact thing for our our binary digit, that instead of mod 10, it would just be mod 2. And instead of dividing by 10 to get the next shifting over of one decimal digit, it'd be dividing by 2 to get the next binary digit. For decimal digits, we knew that we only needed 3 of them. This is an 8-bit value, so we need to have 8 of these technically to make sure we've gotten all the digits here. So that's 3 digits, 4, 5. Oh, let's make sure we have enough spacing. 6, 7, 8. And something we should have added is it's all going to kind of run on top of each other. This is the kind of thing that will frustrate you as you're working on your first programs. Let's print a new line at the end so we make sure it's not kind of running into each other. Let's do 254 again. That should just have the single 0 in it, and it does. At the least significant digit is a 0. 254 11111110. So far, so good. With our unit tests, if this was an actual programming practice, I would probably give you a bunch of different inputs to test. For us, as we're working on it ourselves, we can just do one that works. Then what about for our hexadecimal digits? You guessed it. Instead of doing mod 10, it would be mod 16. Instead of dividing by 10, it would be dividing by 16. This isn't going to look as good as it was before, because as we'll see, it doesn't handle our A's, B's, C's, D's, E's, and F. It's going to give us 14, 15, and 0. Well, we can fix that by actually printing out that digit. That feels like it's kind of cheating, but for our purposes and the interest of time, that gives us our correct result, which is, actually we only need 2 of them, right? Because it's an 8-bit value, we only need 2 hexadecimal digits. So for 254, we get a value of FE back out. Don't let this be my telling you that you only need to test with one value. Certainly try some other values. 128, that's 80 hex. That sounds correct to me. That's just a single binary one. You would want to try it with a bunch of different values. For your programming practices, I will provide you a bunch of different inputs. The other thing we could do is that random number generation and get a result back out. Let's say instead of actually providing an input number, which this was correct, we instead want to provide a random number seed value for us to generate random numbers. Well, first off, we can just say, hey, let's generate a random number instead. So instead of num being something we enter in via scanf, we just do rand number generation for it. We already saw that was too large of a number when we would do a rand number generation. If I want a value in the range 0 to 255, we can take that large number and just do a mod 256. That's the remainder when dividing by 256. It's going to be something in the range 255. And, well, we should probably still have that printf that does the actual value. And now it's not you entered 255 or whatever. It's you generated this number. And this is a good way to test a program because you're not manually typing it in, you're just hitting run. But as we see, random isn't all that random. We do it and we get 103 and then followed by 103 and then run it again followed by 103. The next approach you'll see in a lot of the programs we're working on is that instead of having a single random number or a single number generated, it'll request enter in a random seed value. For the most part, I'll be providing you that code. But this is a way to tell the random number generator each time you run the program, instead do so via a new seeded value, and it should at least give you a different value each time you change the seed value. Now the seed value can really be anything, and there should be no connection between the seed value that you enter and the actual random number that you generate. And if we wanted to instead do all of this now twice, I think I'll be safe to say eventually we'll want to use for loops and whatnot. We can just, for a single seed value now, it should now do the same program basically twice with 2 different inputs. That's a pretty powerful way to test your programs. Instead of typing in the numbers over and over again, you're generating a random seed. That's allowing you to generate as many random values as you want, sufficiently non-deterministic so that you're not just repeating yourself over and over again. I think in the interest of time, we'll end things here. Good luck in PPO2. You're supposed to not get terribly stuck on it, but do let me know where you get stuck. Post questions. I'll be always very happy to respond to them. And hopefully you're enjoying the class so far and looking forward to seeing your submitted programs. Thanks.